Swayam Prabha. Digital India. Educated India.
Hello and welcome to this Manufacturing Process Technology Part 1 Module 19. A brief recap of what we did in the last lecture or last module. We were talking about the energy balance equation on a simple casting problem with two different orientations. One was the vertical gating system, another was the horizontal gating system. We were also discussing about the aspiration effect, which was because of the formulation of a negative pressure at somewhere in the center of the runner, just because of uniform cross section of the sprue. We actually discussed that in such a negative pressure is detrimental to the effect of castings, because to the quality of the castings, because there is a chance of ingassing into the mold because of the high porosity, and various gases like hydrogen and etc. have included in the castings would actually result in a change in strength of the cast. So today we are going to actually look into another interesting effect, which is also known as formation of this vena contracta. So now the situation where the aspiration effect comes into picture is associated with a sudden change in the flow direction. You can see here, this is the pouring basin. This is the sort of a runner which is actually running just perpendicular to the sprue, which is just below the pouring basin, and there is a sudden change in direction of the liquid metal, and because of that there is a contraction which happens, and it contracts around a sharp corner due to the momentum effect. Suddenly there is obviously change in the direction of the velocity. So there is going to be a change in momentum because of the change in direction of the velocity, and this change in momentum would take some time to get formulated. So in fact the flow develops here after some span of length is crossed over by the liquid metal. So in vertical gating this is not really a problem, because basically having acceleration due to gravity, and the problem would be more prominent in the bottom gating or horizontal gating systems. The constricted region 2, as I earlier mentioned, is known as the vena contracta. You can see here, this really is the the radius which would come of the particular stream, and r in fact is the radius here, right about here. D is really the amount of contraction, or d dash by d would be the ratio of the contraction which would happen diametrically. So that is how there is always a tendency of a low pressure formation because of that. To avoid the creation of vacuum around station 2, the mold is made to fit as the vena contracta itself. So the mold is designed like a vena contracta. You can look at the dotted line here, which says how the mold design should be. So tentative mold design, so that this rapid contraction does not take place. If the runner diameter is capital D, as small d, as you can see here, and the diameter at the entrance is d dash, then normally d dash by d is maintained at a value of approximately 1.3. So that is how this and r is really about 15% of d. So that is what are the design guidelines for doing this kind of a vena contracta shaped mold. So the commonly used items which are there in the gating design, which I probably have mentioned earlier, but not to the total details, is the pouring basin, which is obviously the you can see here, right about here, the complete shape here. So it actually contains the liquid metal and reduces the eroding force of the liquid metal stream coming directly from the furnace. A constant pouring head can also be maintained by using a pouring basin. So whatever stresses the mold has to take are really along this region, without letting the actual mold shape being intact or not getting distorted. There is a strainer, which is normally a ceramic strainer in the sprue, which removes impurities or dross. So, it is like a filtration system made up of again a refractory material, a splash core, a ceramic splash core placed at the end of the sprue. You can see right about here, which also reduces the eroding force of the liquid metal stream. So, basically it is a sort of a reinforcement that you are making here of high strength, so that there is no erosion in the sand around the mold. Then there is a skim bob, you can see right about here. It is a trap placed in the horizontal gate to prevent heavier and lighter impurities from entering the mold. Obviously, because of a sort of a outflow of this particular material, there is a tendency of the lighter material to rise on the surface and get collected all here, and slowly because we are talking about a heavy Reynolds number flow. So, there will not be much diffusional migration between the mainstream and this dross collected right about here. Okay. So, that is how the skim bob. So, you have all these different pouring basins, strainer, splash core and skim bob being a part of the gating design to prevent the impurities from going. So, now I would just look at a slightly different variant of the strategy that we did earlier for energy balance on a horizontal gating system. So, there we considered ideal situation where there was no frictional effect as such, and there was no effect because of the velocity distribution, but in unfortunately in the real world you do have this no slip zones and a parabolic flow profile, which results in some loss by itself, and also there is a pipe friction which would be there, because there is a some amount of flow distance that the liquid metal has to undertake in order to reach the mold, and this is through the runner and also the sprue and the pouring basin. So, therefore, there is also a loss because of that, and then there is a energy loss also because of the sudden contraction which would happen in different places, or even sudden expansion sometimes, depending on how the pouring basin is designed with respect to the sprue. Okay. So, because of all these different effects, the actual energy balance equation may vary quite a bit, and that is what we are going to study now. So, in the velocity distribution within the conduit depends on its shape and nature of flow, the laminar or turbulent, and we will assume the friction losses. So, the non-uniform velocity distributions can be accounted for by modifying the kinetic energy term in the energy balance equation by replacing with V dash square by beta, where V dash is the average velocity and beta is a constant for circular conduits. Beta can be treated as for the laminar flow 0.5. Okay. So, this is for circular conduits. So, this is for the laminar flow case further. And can be treated as 1.0 for turbulent flow in circular conduits. So, basically that is how we will try to modify the kinetic energy term, okay, in terms of its different properties of flow within the sprue and runner channels before the metal reaches the actual mold. Okay. So, the energy loss due to friction in a circular conduit, and these are some of the assumptions we are borrowing from elementary fluid mechanics. And basically the more important part that has to be seen here is the application, that how this energy loss is going to change the time of filling, etc., related to the cast. So, I am not going to actually prove how the loss balance equation or how the energy loss balances happens for a circular conduit for a laminar or a turbulent flow case. Okay, but I am going to assume some of the things from elementary fluid mechanics to sort of estimate the time of flow, which is more important here for the liquid metal to go into the mold. Okay. So, on the basis of per unit mass, it is given by energy loss is given by this term EF1, which can be recorded as 4 f L by d V dash square by 2. Again V dash is basically the average velocity, capital D and capital L are the diameter and length of the conduit which is in question. So, I will just write down as diameter and length of the conduit, and F of course is the friction factor. And in fact, is variable based on if the flow is laminar or transitional or turbulent. So, the F depends on the nature of the conduit particularly associated with the conduit roughness and also the flow, the type of flow, whether it is laminar or turbulent. So, while using the integrated energy balance equation between 1 and 2, the EF1 really should be added to the energy at the point 2. Okay. So, if I just were to recall the way that we had set up the horizontal gating problem, I would just so this right here was the vertical gating system designed, where we talked about the point 1 which was somewhere on the top of the pouring basin, and point 2 somewhere at the beginning of the runner, and obviously point 3 which was somewhere just before the entry to the mold. So, that is how we had figured out this vertical gating. Similarly, for the horizontal gating system, if you may recall, we had a pouring basin opening up into a sprue again, which was slightly tapered to avoid the aspiration effects, and there of course was a runner which was designed to enter into the mold as if the mold gets filled up from bottom up, So, it is like that is why called bottom gating system. So, this was point 1, this was point 2, and right about this entry here was point 3. So, that is how we had actually studied both the systems. So, if I were to, in this particular case, use the energy balance equation between, let us say, 1 and 3, then obviously E f 1 should be added to energy at 3, okay, because this is the energy loss that would happen from the overall energy which is available at 1 for the material to be successfully able to withstand the frictional effects on the wall side of the conduit. So, for a smooth conduit, the value of f, again borrowing from fluid mechanics, is given by some empirical quantities of values. So, f is recorded as 16 by Re for laminar flow, probably corresponding to Re less than 2000. So, basically it considers even the transitional as well as the laminar flow both, and the f can be related to again the Reynolds number in a little different manner as illustrated here for turbulent flow. Typically Re greater than 2000. So, I can probably solve this and approximate the total friction factor here f as 0.071 Re to the power of minus 1 by 4 for a Reynolds number mostly turbulent. So, varying between let us say 2100 and very high 10 to the power of 5 or so, which is like quite high Reynolds number. So, we will assume this to be the friction factor, and I am not going to get into the details of how these arrive, because we have borrowed this from the fluid mechanics. So, f basically would be used in our case to calculate what is the friction factor, which will be added again to the 3 side, okay. So, that this is the loss in energy to the energy head that is available at 1 because of the potential head of the material, so that the actual time can be estimated in this manner. So, this kind of brings us to the 2 very important factors which would be responsible for energy losses in the Bernoulli's equation. So, one of them is obviously the friction factor, which is a function of how smooth or rough the walls is, and in a circular conduit we have seen how to estimate that using the factor f, which where f is a function really of the Reynolds number. So, between the let us say for the laminar or the transitional region, f is kind of different, and then for the turbulent region f would be again different. So, barring few cases where the metal head that is available or the liquid metal head that is available is very small, we will mostly use the transitional the turbulent regime for the Reynolds number estimation and simultaneously again determination of friction factor. But only in the case where the metal head available pouring head which is there in the basin is almost towards the end where all the pouring basin metal has been consumed. So, in that case probably there may be an instance where some time delay may happen because of a small amount of metal remaining within the pouring basin, which will probably flow with laminar in the laminar regime. So, there you may have to estimate f in a little different manner. So, having said that, we are wanting to sort of make a final form of equation where the velocity distribution, losses because of velocity distribution or effects because of velocity distribution to the kinetic energy and the frictional factor which I have just calculated have to be incorporated in the total energy balance. So, the other remaining issue which I will like to cover in the next module is basically that because of entrance effects, because obviously the liquid metal here does not have a constant cross section of the conduit while running. The conduit may bend, for example, from the sprue to the runner, or even from the runner to the gate region of the mold, or sometimes there may also be effects because of sudden contraction or expansion of the flow paths. And so, there has to be an energy loss accounted for in the Bernoulli's principle because of that variation as well. So, once we do that, probably in the next module, we will couple all these different losses, that means the effect because of velocity distribution, effect because of wall friction, and effect because of these entrance effects, entrance of the liquid metal into different cross sections, and then put a final formulation which would talk about the correct energy balance, in the real situation. So far what we estimated in terms of time of filling, etc., was really an ideal case. So, with this I would like to close this module and look forward to do the entrance effects in the next module. Thank you.